Let's take a look at how to solve a conduction problem in ANSYS. And while doing so, to understand what's happening under the black box, we will invoke the concepts that we looked at in the big ideas in finite element analysis, where we're looking at one-dimensional heat conduction. Here, we have two-dimensional or 2D heat conduction, so temperature varies in two directions, x and y. And we'll say the conduction is steady, so there's no variation with time. And we have a block, and we are given the boundary value problem here, okay, corresponding to this 2D steady heat conduction. This equation here, which is called the Laplace's equation, represents the energy conservation. And this is in the absence of heat generation. There's no heat generation here. And theta is a dimensionless temperature. So you take the temperature and you non-dimensionalize it this way. So T naught here in the non-dimensionalization is the constant temperature of the bottom face. Okay, so it's the temperature at which you maintain that face. And T infinity is the far temperature of the fluid bathing the right face. So this face is exposed to fluid, and if you move far enough away from that face, you have some temperature for the fluid, and that's what that temperature is. So those are the two temperatures used in the non-dimensionalization. And in terms of the boundary conditions, here T is equal to T naught, so theta is 1, and that's called an isothermal boundary condition. It's just setting the temperature. Here we have, it's setting the heat flux to be 0. It's because the heat flux in the 2D, okay, it's if you need to take heat flux is a vector, and this will give you the heat flux. This will be proportional to the heat flux in the x direction, and that's perpendicular to the face, and so that's set to 0. And here the we want the heat flux in the y direction to be 0, and so that derivative is set to 0. This is also same as that. Both of these are heat flux being set to 0. And this is a convection boundary condition. And here Bi is the BO number, so this gives you the aspect ratio, that it's the block is twice as high as wide, and this is called the BO number, and it's a non-dimensional way to express the convection coefficient. And the convection coefficient gives you a measure of how much heat is being exchanged between the block and the fluid. So for instance, if our fluid was air and we put a fan and we blew the air, we would have more heat transfer happening between the two, and we would represent that by a higher value of H. And this problem shows you the three major boundary conditions you get in a conduction problem: isothermal, convection, and heat flux. So we'll find the temperature and heat flux distribution in the block using ANSYS.